Hi everyone. Again, welcome to another class on quantum theory of many-body systems in condensed matter. My name is Luis Gregorio Dias, here at the Institute of Physics at the University of São Paulo. And in today's class, we're going to discuss the Kondo effect in quantum dots. So it's a follow-up from the previous lecture, where we discussed the transport properties of the Anderson model. And this is more like a seminar, not much as a class. So here we're going to discuss several aspects of the Kondo effect, and in nanostructures and quantum dots is included here. So we're going to start by discussing what is the Kondo effect and what was the so-called Kondo problem in the 60s and the 70s. And how this Kondo problem essentially got solved by different techniques, but chief among them is Wilson's NRG method, the numerical renormalization group, and how we can calculate transport using the numerical renormalization group results for a quantum dot, say, in a Kondo regime. And that's the application. The Kondo effect happens in many different nanostructures, quantum dots included there, and we're going to see how we can detect the Kondo effect through the transport properties, through the properties of the conductance in a quantum dot coupled to metallic plates. All right, so let's dive right in. Okay, so let's talk about the Kondo effect and Wilson's NRG method and how do we apply that for quantum dots. This is going to be more like a seminar than a lecture, but I'll try to be as clear as possible and make connections with the other topics that we studied in the course. So let's see. So the first thing I'd like to discuss is how do we go from atoms to a metal. And so if you have discrete levels in an atom, we all know that. And when we discussed the case of the electron gas, we mentioned that a metal is a system composed of atoms where the electrons are arranged in such a way that when you take the electronic states for the whole system, there are states very close to the Fermi energy, or meaning the energy of the last occupied level in a metal, which are available. So you can, with a minimum amount of energy, promote an electron from a filled state to an empty state. So that's usually referred to as a conduction band. In that sense, what happens if you add an atom where you have an unpaired electron? And here, as we discussed also, this unpaired electron is not just an extra electron. It actually is a magnetic moment, meaning that this can be like, say, an unfilled D level or F level, which is very localized near the nucleus, and so it doesn't hybridize easily with orbitals of nearby atoms, so that they do not form. They form very localized states. So that would be a magnetic moment, a magnetic impurity. Okay, so transition metal atoms or rare earth materials, rare earth atoms also have unfilled F levels in this case, so they are all magnetic. So what happens if you have magnetic impurities and you put these into a metal, right? So this is not like a crystal, it's just impurities in a metal. And the question I'm asking here is whether the resulting compound is still a metal, in the sense that it still have the same properties of a metal. So one of the hallmarks of a metal is the fact that its resistivity has a well-known behavior with temperature. It essentially decreases as the temperature decreases. And why is that? Well, usually the resistivity of a metal, the microscopic factors that lead to electrical resistance in a metal, they all tend to decrease or be less important as the temperature decreases. For example, scattering by phonons is something that we haven't discussed in the course yet, but that decreases with temperature. That the probability of a scattering of electron in a phonon decreases as the temperature decreases. So what happens now if you have a magnetic impurity? You know, a few atoms scattered around, or a few magnetic impurities in a metal. What happens to the resistivity? And it has been known since the 30s and the previous century that if you look, say, at different alloys of metals with magnetic impurities with say, a certain average magnetic moment for these impurities, you find that the resistivity doesn't always decrease with the temperature. It actually reaches a minimum. So this minimum in the resistivity is what is usually referred to as a signature of the Kondo effect. And in the 1960s, it has been established that there is a correlation between the existence of a magnetic moment, or a Curie-Weiss component in the magnetic susceptibility, and the appearance of this resistance minimum here. And that's, for instance, here I have 1% of iron diluted in these different compound alloys of niobium and molybdenum, and in these different concentrations, notice that the molybdenum factor is increasing, means that essentially getting in this sense. So the larger of the molybdenum share, 0.2, 0.7, or 0.8, I'm more into here, into this plateau. So the magnetic moment of the iron impurities in the system actually increases. So when this effective magnetic moment for the iron atoms increase, I have a more well-defined minimum right here when I have a lot of molybdenum and less niobium. Okay, so right there. So this is a minimum in the resistivity, and the question is, why does that happen? So what's going on here is that these magnetic impurities with a sizable magnetic moment, say in this case of 0.9 molybdenum, 0.1 niobium, they do take part in the scattering of electrons of the impurities. So how does that happen? So what happens is that if the temperature is large, there will be essentially, if you measure the conductance here, the electrons will just see the magnetic impurities as scattering systems, right? So there's going to be electron-phonon scattering, but also it's going to be scattering of these impurities here. Okay, and that's suppressed as well as another mechanism that is suppressed, like kind of disorder, right? This is also suppressed when the temperature decreases. But if the temperature reaches a characteristic scale, which I'm calling here the Kondo temperature, the TK, and well below this characteristic scale, what happens is that the spin or the magnetic moment of the impurities starts playing a role. It means that the conduction electrons, they start kind of seeing that there is a magnetic moment there, and they tend to align their own spin anti-parallel to that magnetic moment spin. And here is just a cartoon. Actually, these spins don't need to be pointing in the same direction. Usually they're not. It's like more a paramagnetic ordering. But for every impurity, there will be this correlation between the spin of the electron that comes in and the spin of the impurity. They tend to form a singlet. But this is going to be a many-body singlet. The thing is that in this regime, this spin scattering actually starts playing a role in the resistivity. And that's why the resistivity increases. Essentially, these spin-dependent collisions, if you wish, they start to be more probable. And then the probability of having this spin-related scattering increases as the temperature decreases. And that's what the happens, that the resistivity increases with decreasing temperature. And this is referred to as the Kondo effect. So in this regime of the Kondo effect, what happens is that the fact that you have this formation of these many-body singlets kind of enlarges the range in which these collisions or these this scattering happens, and therefore this allows for more process like that as the temperature decreases. And the typical size related to these scattering lengths, if you wish, or the so-called Kondo length, it has to do with the inverse of the Kondo temperature. So the smaller the Kondo temperature, the larger is this characteristic scattering length. It's essentially the Fermi velocity divided by the thermal energy, the characteristic Kondo energy. Okay, so in this case, we have this characteristic length scales, and we have a sort of a magnetic screening of the magnetic moment by the conduction electrons. So this is a correlated state that usually if the impurities are very far apart, so in the diluted regime, these some people call it the Kondo cloud. I don't like that term very much, but some people call it. And these Kondo clouds around the impurities are very far apart, so they don't interfere with each other in the case of diluted impurities. So let's look at a model that captures this kind of scattering or this formation of these magnetic moments, which is usually called the Kondo model or the SD Hamiltonian. SD coming from S wave electrons in a metal with d orbitals in the impurity. So this is sometimes called also the Kondo Hamiltonian, and we derived that from the Anderson model in the previous class. I tried to remember to put a link here, where we have a conduction band of free electrons, right? It's just a metal. So interactions here are very small comparatively, but you have this single, say, one magnetic impurity that are responsible for the spin scattering. So it would be something like that. So there's this magnetic moment, this S representing an impurity, and this will give matrix elements that will scatter off, say, an incoming electron with spin S and momentum K, and we scatter off to a momentum K prime, but most importantly with a spin S prime that's going to be most likely in the S direction will be flipped. Okay, so this model captures very much this idea of having these diluted magnetic impurities in the metals, and it was studied in the 60s, and in particular by a very famous paper by Kondo, who was a Japanese physicist, and I think he, I'm not sure if he passed away. I'll have to check that. So, but the point is that if, as I mentioned, usually you have these. If you expand the impurity Hamiltonian, you have these terms, right? So these terms coming from, right, you just expand these other, these terms here, you have in different directions, there will be Sy and there will be Z. In the Sy directions, the terms involve this spin flipping of conduction electrons. So an electron with K prime is destroyed, an electron with momentum K, but opposite spin is created, and there's the other process. So this J is positive. So that means that these, if J is positive, these processes tend to favor antiferromagnetic alignment between the electrons and the impurities. And of course there's the free term here coming from the metal. So if J is larger than 0, and I have then the spin flip scattering terms like here, the thing is if you can calculate the contribution of these processes to the resistivity. And that's precisely what Kondo did in 1964. So what he did, and is expressed in this paper, was a calculation for the resistivity, and also the resistance as a function of temperature, using a diagrammatic expansion that is very similar to what we're going to see in later classes in this course. And he did perturbation theory to order of J cube. Okay, so he has to go to this cubic order so that you get the term that is responsible for the minimum. In second order in J, you don't get that. Okay, so for the in this regime, I mean third order in J, the result for the spin contribution to the resistance is written as this, proportional to something like this: J squared 1 minus then 4J rho naught, which is the density of states of the metallic electrons at the Fermi energy, with a log of kBt over d, and d is the bandwidth of the metallic band. I don't think I mentioned that before, but here the assumption is that the electrons are in a conduction band that is essentially squared. It's different than the round one I showed before. That goes from minus d to plus d, and the Fermi energy is precisely at 0. So this is the density of states, rho 0, so it's the same independently of the energy, and the half bandwidth of the band is d, right? So this is like, if you measure this from 0 to the Fermi energy, this would be of the order of electron volts, okay? So in this sense, there's this log dependence of Kb of the temperature divided by this d, which is the largest energy scale here in the problem. Notice that Kbt is small, right? This only appears when Kbt is small, because that's when this log becomes large enough to be larger than this one. And in fact, if you add the other terms here, the other processes that usually scale with the fifth power with the temperature, so it decreases with temperature, with this other term, then at some point you get a minimum, right? So you have a positive contribution, this negative contribution, which increases, and at some point this reaches a minimum. And the minimum of the temperature, what Kondo showed, is that goes with the concentrations of the impurities with the power 1/5, and also depends on these other prefactors. But this is something that was experimentally measurable. Notice that this T minimum is not the Kondo temperature, right? This is sometimes a confusion that people make, but they are different. In fact, the Kondo temperature is defined at the point where this expansion diverges. Notice that if Kb, this is a minus log of Kbt over d. So if Kbt goes to 0, this log explodes and the whole thing diverges. So there's something, perturbation theory gets you the minimum, explains why this is going on, but definitely doesn't explain what happens for temperatures well below T minimum. And the only free parameter of this theory is this Kondo temperature, which is defined as this. So it's exponentially small depending on the value of the density of the electrons at the frame energy. So this is an important point. And this is the reference for the paper. Now, the model that I just described is valid for diluted impurities. So that means that the magnetic impurities are far from each other. Now, if they are close to each other and actually forming a periodic structure underneath these coupled to these metallic electrons, then we have a different problem, a slightly different one, that I'm not going to concentrate here in this lecture. But this is the so-called Kondo Lattice problem, which appears in heavy fermion materials, for instance. So the Kondo impurity model is not suitable to describe these materials. You need now something extra, like perhaps treating these. You might even treat these impurities in mean field and do some dynamic mean field, and the Kondo model would be like the impurity model to be solved, but you just have to be careful. So these Kondo Lattice systems, they include materials such as uranium-based and cerium-based compounds and other newer materials as well. But usually these electrons are localized in 4F or 5F electrons, like rare earth materials and so on. And there's a rich physics in these materials. There's superconductivity. There's even Kondo-like behavior in the susceptibility in the specific heat and so on. So, but I'm just citing this because this is an important class of materials, but it's not related to the diluted limit that we're looking at. So let's give a sort of a timeline of the history of the Kondo effect. So as I mentioned, in the early 30s, there was this measurement of the resistance minimum in some metals. In the 60s was these minimum was known to be correlated with the presence of magnetic moments. But in the early 50s, there was also theoretical work on impurities in metals. And the work by Friedel, for instance, on these virtual bound states, which was an important piece that was later later used in the explanation for the Kondo effect. Now, in the 60s, there was a lot of advances, both in the experimental side, but also in the theory. So in 61, there was the Anderson model for magnetic impurities in metals. That's when Phil Anderson developed his model. And then in 64, the ST model appeared. The Schrieffer-Wolff transformation was around this era as well. And in the 60s, I think it was 66, I have to check. But there was the solution for the Kondo, the perturbation theory and the contribution to the resistivity in 1964, as I mentioned. In the 1970, there was Anderson solutions, so-called poor man scaling, which gave an interesting view of how you could get those log divergencies in the resistivity that became known as the Kondo problem. And in the 70s, around 75, for instance, that's when the Review of Modern Physics by Ken Wilson came out, where he laid out the basis for his numerical renormalization group, which is not perturbation theory, and you could describe not only the onset of the Kondo effect of the magnetic screening of the impurity by the metallic electrons, but also do it in a way that involve no divergence. So that's in this in here that's when we will focus Wilson's NRG method. And in the 1980s, actually there was an exact solution of the Kondo problem and the Kondo Hamiltonian in terms of the Bettian sets. So that's the Nathan and Andre's work, and others, including Professor Kyoko Furuya, who was a professor at Unicamp. He also contributed to those works. So let me focus on this, the idea for Ken Wilson, who actually got the Nobel Prize in Physics in 1982 for his work, not only in the Kondo problem, but in many other works in critical phenomena and phase transitions, and the application of the renormalization group to these problems. So let's take a quick view of what Wilson's NRG is all about. So what's going on here in terms of these impurity, this contribution from the impurity to the resistance, and why does it diverge? Well, it diverges because of this log, right? So it diverges logarithmically for t going to 0 or the bandwidth going to infinity. It means that below a certain characteristic energy scale, t minus tk, this expansion breaks down, and the perturbative expansion doesn't hold anymore, meaning that the terms that come after that will be larger and larger. So perturbation theory breaks down. Okay. Now, of course, the experiments show a finite R at 0 temperature as t goes to 0. So this is a problem of the theory. Okay, and why does this log comes about? Oh, it comes from a cutoff, right? A small energy cutoff to an integral like this, d epsilon over epsilon. And so you say, okay, if the temperature is small, and I can now do this cutoff, and I'll get the log. The thing is that the temperature is too small. This log goes to infinity, and this is not a very good way to treat your problem in this regime. So here it's important to notice that when I make an integral like that of 1 over epsilon, all energy scales contribute, and so if you do a cutoff, you run into problems. So what do I mean by all energy scales contribute? So let's take a very simple example here. Let's try to calculate the integral of 1 over epsilon on a grid of, say, size delta. All right. So essentially, I'm going to calculate this integral. What if I do this integral from, say, 0 to 1? That's the one that I want to integrate, and I do this grid on regular spaces, right? So say my delta here is 1 over 8, and now I'm gonna add all these areas here. So if I do that and calculate the area on each of this bin, I get something like that. So I can actually do the actual calculation, right? So this is delta, and I know 1 over epsilon. So the area here is log of 1 minus delta 1 minus n. So this is a 1, a 2, a 3, a 4, 5, 6, 7, and 8. So this is my definition. What does it mean? Here, see, as n increases, this area increases. So here is actually infinity, right? Essentially because 8 times delta is 1, and I have a divergence. So at some point, my computer will complain about this because I'm trying to add these areas, but this one is infinity, so I cannot do. Okay, say, all right, so let's do a cutoff. Well, the cutoff will still have a small area here that's, even if I increase n and put 100, the last slice will also be infinity, right? So I cannot never get the result okay. So this is not a good approach, meaning that The fact that the areas keep increasing as I go towards zero is definitely not what I want. Now what if I take a different approach? Instead of having regular spacings, I take a logarithm, or like a exponential, decreasing the delta decreases exponentially with n, right? So for n equals 0, this is 1, right? So for n equals say, let's see. So let's take this as 2. This big lambda here is 2. N equals 1. This is 1/2. So that I mark it here. So this is, you would have to figure out this distance, but this actually should be proportional, not equal. But and then the next one would be 3. That's 1/2 to the minus -2. Sorry. That would be 1/4, 1/8, etc. So if n goes to infinity, very large, I keep approaching the 0 here, right? So it's pretty much the same as before, that for large n's I approach 0, and the integral should approach the actual integral, right, of 1/epsilon. But this is a much more controllable approach, because all these areas here, they are the same independently of n. So they will be just log of this constant, right, log 2 here. And you can convince yourself that this should do. So if I have 1,000, well, the last area that I'm missing, I'll be missing, I'll just miss a log of 2 here. So I'll have a much better chance of capturing this integral numerically than if I do the other approach of regular spaced intervals. So that's the whole idea of Wilson's method. So he takes this problem, and he noticed that the problem is not with the perturbation or the interacting term. The problem is how you treat the conduction band electrons. And that's the whole rationale behind his numerical renormalization group. So again, this is the density of states, and in my approximation, the density of states is not going to be circular like this one, but it's going to be squared, but this doesn't matter. But the whole point is that the Kondo effect happens in energies very, very close to the Fermi energy. So that's when the log divergence happens, right? So it's like the divergence happening here when you approach 0. That's when this last area will explode. Same is similar to here. So the contributions from these spin scattering, they get stronger as the energy scales approach the ones at the Fermi energy. Okay, so the temperature going to 0, meaning that the Fermi distribution gets more and more flat around the Fermi energy, and that's when you run into these problems. So Wilson's approach is, okay, now let's treat the density of states here and discretize it, not in the regular sliced way, but in a logarithmic way, to try to avoid to get these log divergences. Now there's another element which is also crucial in Wilson's approach that has to be with numerical accuracy. Alright, so you can discretize, your band in a more appropriate way, but can you numerically calculate things at those very small energy scales accurately enough to provide good results? And so this is a very subtle point, but he makes it, he explains it very well in his original paper. So let's start with an example, right? So imagine that you have a Hamiltonian H naught, and you can calculate its energy levels with 5% precision in the energies, right? So yeah, nowadays you can get much less than that, but let's do it this number just to give you an example. Now imagine now that I have this Hamiltonian perturbed by, say, a H1, say that this is a two-level Hamiltonian, and this H1 also is a two-level Hamiltonian if you wish, but it couples these two states, so I have splittings here in these states, and these splittings are about 1/10 of the original H0. So this is good perturbation theories, right? So the typical energy scales from this Hamiltonian is about 1 electron volt, and this is 1/10 of that. All right, so you do that, and then you add another perturbation here, which is 1/10 of that. So the splittings will be 0.01 electron volts. So this is 100 times, the energy scales here are 100 times smaller than this one. So this is a nice perturbative expansion. Okay, now can you calculate these splitting accurately? And this is a question. If your machine only gives you 5% accuracy in these in your diagonalization, if you wish. Well, let's try it. Okay, so if I come here and diagonalize any Hamiltonian at this scale, I'll get a 5% error, so around 0.05. Okay, so that's the brute force approach. Say, okay, well, yeah, let's just take this and diagonalize it, right? So calculate the matrix elements and let it run. What do you get? So if you do this brute force approach and you just direct diagonalize, well, your accuracy will not get any better, right? So you still get an error of around 5% over these splittings, which will be your large splittings. So this 0.05 is 5 times the size of the splitting you want to resolve. So no, you'll not be able to resolve it at this stage, and because you're 500% off, essentially your uncertainty window is of this size. So you say, oh well, but with my computer I don't get 5%, I get, say, 0.1%, something like that. Well, that only tells me that at which point in the perturbation expansion you run into troubles in calculating these splittings, right? It might be in the 10th order, but you definitely cannot go indefinitely in this brute force approach. So let's see how Wilson approached this problem. And what he did is he essentially noticed that the fact that you have this 0.05 here is because you were including the off-diagonal terms in this calculation, and then the fact that you have off-diagonal terms, when you plug that into the routine that diagonalizes the matrix, that's what gives you this 5% error. But what if, instead of doing this, you first obtain these states with this energy, and then you rewrite H0 in that basis? Well, in that basis, H0 is diagonal, right? And now what do? Now you take a basis for H1, which you could in principle calculate H1 only in this basis, and you can calculate that with a 5% error on the energy scales of H1. So if the typical energy scales of H1 is 0.1 electron volts, your accuracy would be 0.05, right? And now you construct H1 tilde that is written in this basis, where you have the diagonal parts that you already calculated from this, but you diagonalize H1 in these new bases. But the uncertainty in diagonalize is still 5%. But now, instead of an error of 0.05%, your error in the diagonalization of this guy is 0.005%. So you improved your resolution, and the only thing that you did is to use the basis that you had calculated before as a new basis instead of using the same basis for H1 as that you use for H0. Okay, so this approach improved your accuracy. Okay, and now your uncertainty of the calculation is still 5%. Okay, so you can keep doing that. Right now you know you diagonalize H1 tilde, so you can use those states to construct the basis for H2, right? Essentially doing this cross product between the bases of the previous Hamiltonian that you diagonalize and the new one. And this, the Hamiltonian will not be diagonalized in this basis, but it will be in this one. So the only thing that you need is to diagonalize in this new basis, so your uncertainty would still be 5% on the next energy scale. So if you do that for H2, right, so you had your energy here, you construct your new basis for which is the one that you obtain for H1 times CD, in which spans the Hilbert space for H2. H2 is not diagonal, but you can calculate its matrix elements and diagonalize it within 5%. So, but 5% of the energy scales of H2. So your accuracy now is 0.005 electron volts, so you can resolve these splittings. So this is the idea of diagonalizing first and using the resulting basis to construct a new basis. That's one of the other important hallmarks of Wilson's NRG. So let's use these two key ideas in the Kondo ST Hamiltonian. One is to discretize the conductance band in this logarithmic scale, right? So I slice up this band in different areas, but I slice it in a logarithmic way, all right? And then once I do that, I map my Hamiltonian, which was a continuous Hamiltonian in here, to a discrete case in the form of a linear chain. And this is like Fourier transform these guys into Vannier-like states, and only one of these states will couple to the impurity directly. That's the F0. So this is discuss how to do it in the original papers by Wilson, but in many other papers as well. So this is the first thing that you need to do is to discretize the band and form this Hamiltonian. So just to give you an idea of what's going on here, you have the impurity coupled to electrons in all of the energy scales of the impurity band in principle, right? And then you discretize it, and then you take only one state per bin. And that's the crucial approximation in Wilson's, that he takes only one state from each of these discretized bins, but still he takes infinite states because he takes from all bins all the way down to very small energy scales, where he wants the resolution to be larger here, right? So that's why he's doing that. And then he maps this into a tight binding chain where you have the impurity at one end and these Vannier states that I mentioned at each extra site. So this is not real space exactly, but is a mapping of these states into a linear chain. But also this will also give you your Hamiltonians, because when you do this mapping, these hopping parameters will decrease as they go away from the chain, meaning that here I'm already setting up the perturbative expansion, which is I add sites to this chain. The energies will be exponentially reduced as I moved away from the impurity. So this is a nice way of expressing this, because now you have a very clear hierarchy of energy scales. So as I mentioned before, this logarithmic discretization is key to avoid these divergences for energies going to zero or low temperatures. And then once you map into this linear chain, you also can use the other idea of mapping, of solving these Hamiltonian in iterative form to get accuracy even at these very low energies. So that's the iterative numerical solution proposed by Wilson. And once you do that, you are actually going down to energy scales in an exponential form. So this is very powerful. So as it turns out, you can define a recurrence relation between the Hamiltonians as you increase the number of sites in this chain that you composed. So if you have the Hamiltonian for n sites on the chain right here, you can write the Hamiltonian for n plus 1 sites as this, plus this extra term here that only involves the couplings between n plus 1 and n plus 1. So we're adding a site to the chain. And as I mentioned, there is this hierarchy of energy scales. So the energy scales of this term will be much smaller than the energy scales of this term here. Exponentially smaller by 1, right? So this would be like H0 and H1 in that example that I gave you. Okay, the thing is that you cannot keep this construction forever. You have to cut the number of states at some point. Why? So, as I mentioned, you start from a Hamiltonian, let's call it H0, which has, say, 4 states on a basis. Then you go to H1, H0 plus H1, and H1 has another 4 states. So the number of states here is 4 times 4. You construct the basis here is 16, right? Or if you want, start with just a 2-level system. 2 times 4 now is 8. Then you add H2, which is the next one, lower energy scales and so on. But here you get 4 extra states, essentially the same 4 states for a charge and spin Hamiltonian, right? 0 up, down. So now you have 32, and you keep going. And when you have the n equals 20, you already have 10 to the 12 states. So if you have 1 byte per states, you might have a few hard drives just to store the basis. So this is impractical, right? And if you try to go to n equals 100, which is very typical in energy calculation, this is over the number of atoms in the universe. So it's out of bounds, essentially. So you do have to cut up the basis and keep that in an acceptable number, say 2000, 1500 or so. And so that means that you would have to diagonalize a 4000 by 4000 matrix, which is still doable, but you have to do it many times. So I have my series of Hamiltonians. So I go and diagonalize my first one, say H0. And then I renormalize the energies. So I just bring it to the energy scale of H1, the next one over. Add H1, diagonalize it, and then I truncate. If I have, say, a number of states maximum that I want to keep, I just keep the lowest energy states. So once I do that, I add H2, and then I multiply this by 4. So I keep doing that. I renormalize that, and I keep doing these diagonalizations. And because of the procedure that I explained, I retain the same accuracy as I had before in percentage terms. So I'm now going to lower energy scales because I'm increasing the number of sites in this chain, but I'm doing is in a very controllable way, and so I keep my accuracy in terms of describing states in the same percentage as in the first one. So I'm in absolute terms in energy, I'm getting more and more precise as I go down in energy scales. The price for that is that I'm throwing away states, right? I'm throwing away states. So, but at least I'm retaining the ones that would be more important for the renormalization group flow. So this is essentially what I'm doing. I'm going from Hn to H+1, and I'm keeping the low energy states. So the question is, we definitely can apply this procedure to the Kondo model, but can we apply it to the Anderson model, and which we studied in the course, right, for the last 2 weeks? And in fact, we can, right? We know that this has an impurity Hamiltonian, which is going to be our H0, and then you can discretize the conduction band, and at the end, you're going to have a Hamiltonian which has essentially the same structure as you had before here. And in principle, you have many properties of the renormalization group transformation when you do that. So you go from N to N1, that's a rescaling plus adding these extra terms. And you might even get what in the RG language is called a fixed point, when the rescaled spectrum of these points does not change anymore. And for the Anderson model and for the Kondo model as well, that's precisely what you get. So if you do that procedure that I outlined, so here I'm increasing the number of sites in the chain, in the NRG chain, the Wilson chain sometimes called. These are U and U over gamma, the parameters that I have. So I'm at 60 sites with lambda here is equal 2 probably. So the energy scales that I'm studying here is 2 to the minus 60 relative to the Fermi energy. So very tiny energy scales. And if I look at the spectrum that I get from these Hamiltonians, all rescaled by energies, I notice there's a change. In this region, there is the spectrum is very similar in this region. Is also similar in this one. So the energy levels, as I change, say add 5 sites, they do not change much. And here too, right? Here more, this is more like an unstable fixed point. But these are the fixed points, the point where the spectrum, the many-body spectrum, doesn't change much. So in the RG language, you can think of these fixed points in parameter space, say U in one axis and gamma in the other one. So this is local moment for gamma equals 0, say in U very large. And then there's the strong coupling, or the Kondo fixed point, and this is the free orbital where when U is equal to 0. So you sort of start on this one, go to the local moment one, and then at very low energies you flow, and that's the term, to the strong coupling fixed point. And you can see all these 3 fixed points in the spectrum of the RG. So this is the free orbital, this is the local moment, and this is strong coupling. And the Kondo temperature would be the energy scale where you transition into the strong coupling case. Okay, so what else can you calculate besides the spectrum? Well, you can calculate the spectral function. And why? Because here in this method, you have the full many-body spectrum, or at least an approximation to it at each energy scale that you have. So for each omega, where omega is the excitation, you have the states. So you can calculate the excitations, I mean the matrix elements between these states, and you can write the spectral function, the minus 1 over pi, the imaginary part of the retarded Green's functions, in the Lyman representation, and all that you need is the matrix elements of the say the C or C dagger operators in the dot, which you can also calculate with NRG. So if you have the spectrum, you can write in the Lyman representation, and you get all these matrix elements and also the energies. So you have, in principle, a whole bunch of sums with delta functions here. So I suggest you look at the class where we talked about the Lyman representation, and you can convince yourself that if you have the spectrum and you have the matrix elements, you can write the spectral function. But there's a technical problem that, if you want for a frequency that is not precisely falling into these energies, this gives you a problem because you have only these peaks. But there's different ways to get a continuous curve, and you need to broaden these delta functions, and there's different choices for broadening functions. This is one that I usually use in my code. A log. This is a Gaussian and a log scale, and that gives me spectral functions like this. And so this is an actual calculation for the spectral function for NRG at the particle hole symmetric point, different values of U, and the width of the central peak means the Kondo resonance. So let's take stop a little bit here and just discuss the features of this plot. So this is a spectral function, right? So I would expect peaks whenever I have these many particle energies. And so there's these two broad peaks here, centered precisely at ED and ED plus U. So these are the two single particle states, remember, for the Anderson model, E and this E plus U. So if I have two electrons here, I have one in this single particle level and one here, so the total energy would be 2 epsilon 1 plus U. But now I have this extra peak here sitting precisely at the Fermi energy, where the Fermi energy of the bath electrons. So what is that? So this is definitely not a single particle resonance, a single particle state. This is a many-body state that appears in the spectral density. Has a much smaller width than the single particle ones. The width of these are related to gamma, right? So the broadening of these levels. And this one has a characteristic scale which has to do with the flowing into that strong coupling fixed point. So if I do this in the logarithmic scale, this would be like a smooth curve going into this value here. And the point where it goes kind of halfway into the value here is about the Kondo temperature. So it's much smaller than U, it's much smaller than gamma, so it's one of the smallest scales in the problem. But Wilson's NRG does a very good job in capturing this because it has very high precision precisely at low energies. That's one of the features of the method. And it is able to characterize the spectral function, this should be A, sorry, at very low frequencies, which means that I have a way to calculate the full spectral function coming out of the Kondo, the Anderson model, with no need to do mean field or perturbative approaches. And the spectral function is so important that it's right in the cover of the book on the Kondo problem, which is the book by Alex Hilson. So that, you know, this figure here is very important in this topic. So to give you a summary of the energy method, is designed to handle quantum impurity problems, and all energy scales are treated in the same footing. Is non-perturbative, so it can access transitions between fixed points in the parameter space, and allows for the calculation of physical properties. And I'm going to give an example in the next 5 minutes to give you an illustration how you can calculate things. So as I mentioned, one important application of the Anderson model in current, say, setups for where we have nanostructures and many manufactured small-scale devices is in quantum dots in the Kondo in the Coulomb blockade regime, which I mentioned in the previous class. So this was called the revival of the Kondo effect 20 years ago, when we started rediscovering the Kondo effect in these systems. So let me give you a walkthrough of how the Kondo effect takes place in quantum. So I mentioned this model in the class on the Coulomb blockade or in the transport properties of the Anderson model. So if you have a quantum dot, you essentially have a region in space where these electrons are confined, say in a semiconductor heat structure. So you have not only quantized levels here, but they are also coupled to a continuum of states on both sides, and there is charging terms here. So if you are in the Coulomb blockade regime, meaning that the electrons in the leads are essentially find this Coulomb barrier to go into the quantum dot, which essentially functions as a small capacitor. That means that your conductance should be small whenever the Fermi energy is not aligned with one of the states in the dot, and we discussed that in the previous class. Right. So if you have a situation where the level is close to the Fermi energy, then you could have a process where it goes from here to here and then to here. But if this is far away from the Fermi energy, then this process is suppressed. But if I align the level with the Fermi energy, then I have conductance, and as a function, say, of the energy of these levels, which is controlled by a gate voltage, I could see peaks in the conductance. That's the Coulomb blockade regime. And every time there's a peak, it means that the number of electrons inside the dot change by 1, okay? Because the average number of electrons here now makes the low energy, the lowest energy is obtained when you have 1 electron more. So you can keep doing that and going from an even number of electrons in the dot to an odd number of electrons and so on. But if you have an odd number of electrons, then what you have is essentially a magnetic moment here. And that's where the Kondo effect takes place. So if you have an odd number of electrons and you go to another one, you now get an even number of electrons. But right in this case where you have an odd number of electrons, if your temperature is small, even if you are right here and no tunneling is allowed, essentially you are in the middle of the Coulomb blockade valley, you might still have transport. Why? Because if you are at temperatures below the Kondo temperature, that there will be this antiferromagnetic coupling between the conduction electrons and the magnetic impurity, which is in this case this magnetic moment in the dot, or this extra electron here, and that will create a peak right at the Fermi energy coming in the spectral function. Right there, these are the other two peaks with gamma, but this one is sitting precisely at the Fermi energy. And if this sitting precisely at the Fermi energy will allow for transport of electrons. So it means that even though you are not with any resonance, single particle resonance with the leads, there will be conductance here at low temperatures, below the Kondo temperature, because of the appearance of this many-body state. And that's how you measure the Kondo effect in quantum dots. You see this increase in the conductance as you go to a temperature lower than the Kondo temperature. So you have this enhancement of the conductance, which we calculated in the previous class as well. And if you can calculate the spectral function to express the presence of this Kondo peak, then your conductance should also show that. And that's what was discovered in 1998. That was the first experiment where they saw a increase in the conductance as the temperature decreased for only when you had an odd number of electrons in the dot. That's the Kondo effect in the dot. So the quantum dots allows for controllable investigations of the Kondo effect, and this is essentially the result, the experimental result. If you are in the even number of electrons in the dot, and you decrease the temperature, essentially the conductance decreases. Now, if you're in an odd valley, you decrease the temperature, say from down to 25 millikelvin, your conductance will increase, and will increase in a way that is very compatible with what you would expect for the Anderson model in the Kondo regime. And in fact, this curve here represents a calculation using NRG. So this is an example of course, this has been seen in other experiments throughout the years, and that's not only in quantum dots but other systems as well. And is a very nice and clean application of what we have seen in terms of the transport properties of the Anderson model that we can calculate in linear response. So that's it. I hope you liked this class and was more like a seminar, but hopefully it was clear enough so you could follow it and make a contact with what we have seen in the previous classes regarding the Anderson model and transport properties in linear response. So that's essentially closes this chapter or this part on the Anderson model for the course. And let's keep going. Hope to see you in the next class. See you.